Warning. This episode may cause sudden moments of clarity and uncontrollable urges to redesign everything. You've been warned. This is mechanical engineering made simple.
I love that wording. It is very fitting for today.
Right. Welcome, everyone. We are inviting you on a special deep dive into a text that, honestly, on its surface, looks like a standard, maybe slightly intimidating academic chapter.
Oh, definitely intimidating.
Yeah, we're looking at chapter 11, which is specifically focused on the chemistry of combustion.
Yeah.
And I know hearing chemistry and combustion in the same sentence might sound like a recipe for, well, a really dry lecture.
People usually zone out right about there.
Exactly. But I promise you, what we are about to uncover is going to completely change the way you look at the physical world around you. We're going to fundamentally tear apart everything you thought you knew about fire, fuel, and how engines actually work.
It really is a paradigm-shifting piece of source material. I mean, we interact with combustion every single day of our lives.
Oh, absolutely. Every day.
You turn the key in your car, you flick a lighter, you turn on your gas stove to boil some water, or, you watch a rocket launch on the news. We take the resulting fire entirely for granted. But the underlying physics and the chemistry of what is actually happening in those moments is just profoundly beautiful and incredibly precise.
And wildly misunderstood by the general public, I'd say.
Completely misunderstood, yeah.
And that brings me to the core question I want to pose to you, the listener. I want you to really think about this for a second. When you picture a car engine burning fuel, do you think of it as creating heat?
That's the trap right there.
It is. Like you have this cold liquid gasoline, right? A spark goes off and suddenly, poof, heat is magically generated out of nowhere to expand the gases and push the pistons.
It's how everyone pictures it.
Because if you do think that, you're not alone. That is just the intuitive way our human brains process fire. But today, in this deep dive, we are going to absolutely shatter that illusion.
You really are.
We're going to look at combustion, not as energy transfer, which, is just adding heat from somewhere else, but as energy transformation.
That is the essential premise we need to establish right at the top. Every single ounce of energy that powers a heavy car down the highway or pushes a massive rocket out of Earth's gravitational pull.
Which is a crazy amount of energy.
Right, massive amounts. All of that energy is already packed inside the unburnt fuel mixture sitting right there in the tank.
Wow.
The spark plug in your engine doesn't create anything. The spark doesn't make energy. It simply unlocks a microscopic vault where the energy has been hiding all along, just waiting to be released.
Okay, let's unpack this.
Yeah.
Because that is a huge conceptual leap for a lot of people. To understand this vault, we really have to talk about what we're calling the great combustion misconception.
Yeah, let's get into that.
And we also need to talk about what we're going to call the energy ledger throughout this deep dive. Because our source material points out that mechanical engineers are actually trained to think about this wrong right from the start of their education.
They really are.
They rely on this theoretical model called the air standard cycle. And when I read that, I immediately wondered, why are we teaching engineers a flawed concept?
Well, I wouldn't say it is necessarily flawed. It is just an extreme simplification.
Okay, a simplification.
Yeah, the air standard cycle is a theoretical model used in engineering to just make the math easier. It treats engines simply as heat engines.
Oh, yeah.
So in this simplified macro model, combustion is just viewed as a mysterious black box where heat is magically added to a working fluid, like air.
Just boom, heat appears.
Exactly. And that heat causes the air to expand and do work. It's a convenient shortcut if you just want to calculate rough thermal efficiencies, but, it completely ignores the reality of the physical universe.
Yeah, it definitely encourages this false narrative that combustion is just a process of pumping thermal energy into a system from the outside.
Right. It skips the actual chemistry.
Yeah. It's like pretending money just magically appears in your bank account without thinking about the actual job you had to do. The hours you worked, the taxes you paid to earn it. It just skips right to the final balance.
That is a perfect way to put it.
The reality, as this chapter so brilliantly lays out, is that the energy released during, say, a spark ignition engine's combustion comes entirely from breaking and reforming the physical chemical bonds holding the fuel atoms together.
It is all about the bonds.
Yeah. And to help you, the listener, visualize this, I want you to think of fuel molecules like a sturdy box packed completely full of tightly coiled springs.
Oh, I like that analogy.
Right. The springs are compressed, they're shoved in there, storing all this kinetic potential energy. The spark from your spark plug isn't a heater warming up the box. The spark is simply the physical latch that opens the box and releases the springs.
Yeah.
Bam! The box opens, they expand, they fly outward. And that violent release of stored physical tension is the exact energy that drives the piston down.
What's fascinating here is how this completely flips our entire perspective.
It really does.
We are moving away from macroscopic thermodynamics, where we just look at the temperature and pressure of a gas, and we're zooming way, way into microscopic chemistry.
Like down to the atoms.
Exactly. We can no longer just look at a thermometer. We have to look at bond energy. Bond energy is literally defined as the minimum amount of energy required to separate a molecule into its constituent atoms.
And the text gives us this incredible visual, figure 11.2, to explain how this bond energy actually functions on an atomic level.
That figure is crucial.
I want you to imagine two atoms floating in the vast, empty void of space.
Let's visualize that in detail for the listener, because understanding this is the key to everything else we're going to talk about.
Go for it.
So imagine these two atoms are infinitely far apart. Now, in physics, infinity just means they are far enough apart that their electromagnetic fields have absolutely zero influence on each other.
Okay, so they're totally isolated.
Right. At that distance, their potential energy relative to one another is zero. But as they begin to drift closer together, microscopic forces come into play.
Which forces?
Well, there are attractive forces pulling them together. The positive nucleus of one atom is naturally attracted to the negative electron cloud of the other.
Makes sense. Opposites attract.
But simultaneously, there are repulsive forces pushing them apart, because their two negative electron clouds repel each other.
Ah, right. Like repels like.
Exactly. So as the distance between them decreases, these warring forces cause their total potential energy to fluctuate and change.
It's just like bringing two really powerful magnets closer together, right? Like if you try to push the north poles together.
Yes, perfect example.
You can physically feel that invisible magnetic tension in your hands, pushing back on you before the magnets even touch.
Precisely. And figure 11.2 shows this graphically. As the two atoms get closer, the attractive forces initially win out. So the potential energy of the pair dips down into a deep valley, a minimum point on the graph.
So they sort of fall into a groove.
Right, that specific point of minimum energy is the sweet spot of equilibrium. That is where the molecule is stable, and that is exactly where a chemical bond forms.
Okay, so a bond is just equilibrium.
Yes. The bond energy is the mathematical difference between that deep, comfortable valley of equilibrium and the baseline zero energy state from when they were infinitely far apart.
Wow.
So if you want to break that bond, you have to put in exactly enough energy to drag those atoms up out of that valley and push them all the way back to infinity.
So if all this immense energy is physically trapped in these chemical bonds, these microscopic valleys of equilibrium, how do we calculate exactly how much is in the vault for, say, a whole tank of gas?
Well, we can't just guess.
Right. This is where we have to become essentially chemical accountants. We have to meticulously balance the ledger of atoms.
And that ledger is defined by a very specific, very crucial formula in thermodynamics. It's called the enthalpy of formation.
Right. Enthalpy of formation.
It's represented by the symbol delta H sub F. Simply put, this is the net energy required to form a compound from its raw base elements.
Okay, give us the formula.
The formula for the ledger is this: atomization energy minus dissociation energy minus resonance energy minus latent heat.
Okay, I know that sounds like a massive wall of academic jargon for anyone listening.
That does sound like a lot.
But I promise, when we break it down into an accounting ledger with expenses and income, it makes total intuitive sense. Let's start with the very first term on the ledger, atomization.
Atomization.
To build a fuel molecule from scratch, you can't just mash giant chunks of raw materials together. You have to break the raw elements down into individual gaseous atoms first.
Yes, think of it like building a very specific Lego castle.
Everyone loves Legos.
Right. But you can't start with smaller pre-built Lego walls or cars. You have to break everything down into individual single Lego bricks first.
That makes total sense.
Let's take a standard hydrocarbon fuel. The base elements are just carbon and hydrogen. But in their natural standard state, which chemists define at 25 degrees Celsius, and standard atmospheric pressure carbon exists as solid graphite.
Like pencil lead.
Exactly. And hydrogen exists as a diatomic gas, H2, meaning two hydrogen atoms naturally bonded together.
Okay.
Before you can build a new fuel molecule, you have to spend energy. You have to put heat in to vaporize that solid graphite block into a cloud of individual floating carbon atoms.
That sounds like like it takes a lot of effort.
It does. And you also have to spend energy to physically snap all those paired H2 molecules into separate single hydrogen atoms. This upfront cost is your atomization energy.
So on our chemical accountant's ledger, atomization is a massive expense. It goes straight in the red.
Just in the red.
We have to pay this energy cost out of pocket before the reaction even really starts.
Yeah.
But then comes the big payoff, right?
Yeah.
Dissociation energy. Now, I have to admit, I found this part of the textbook a little confusing at first. The text uses the word dissociation here in a way that feels pretty counterintuitive.
How so?
Because dissociation normally means breaking things apart. But here it's talking about the energy associated with forming the new chemical bonds.
Yeah, it is a bit of a linguistic quirk in chemistry. It's referring to the bond dissociation energy,
Okay.
meaning it's the energy it would take to break the newly formed bond. But because we are running the process in reverse, we are actually forming the bond, that exact same amount of energy is released out into the universe.
I get it now.
When those free, highly energetic individual carbon and hydrogen atoms finally find each other and snap together to form our new fuel molecule, they drop down into that deep energy valley we talked about earlier.
Right, the sweet spot.
And by dropping from a high energy, unstable free state into a lower stable energy state, they must release the difference as pure energy.
Which goes on our ledger in the black. It's pure income. Well, wait, I have to step in and push back on this for a second because I want to make sure you, the listener, are tracking with just how wild this concept really is. Are you seriously saying that in order to get energy out of a fuel, nature first has to spend energy violently tearing the basic carbon and hydrogen atoms apart?
Yes, that is exactly what happens.
That's crazy.
It seems entirely paradoxical at first glance, I know, but it is a fundamental, inescapable law of chemistry. We are talking about fuel molecules existing in what is called a metastable state.
Metastable. Okay, explain that.
Imagine a giant, incredibly heavy boulder resting in a tiny, shallow crater at the very peak of a massive mountain.
Okay, I have the picture.
The boulder is technically stable in its little crater. It's not rolling anywhere on its own. That boulder is your unburnt fuel sitting quietly in your gas tank.
Okay.
It has immense potential energy because it's perched at the top of a mountain, but it's physically trapped in that tiny dip.
Okay, I see where this is going. If it's trapped, the potential energy is useless to us.
Exactly. It can't do anything for you. To get the boulder to roll down the side of the mountain and release all that massive kinetic energy to crush whatever's at the bottom, you first have to push the boulder up and out of that small, shallow crater.
I have to heave it over the edge.
That initial upward push is the activation energy. It's the energy of atomization. You have to put energy in. You have to spend effort to destabilize the existing bonds.
Wow.
But the moment it crests the lip of that tiny crater, gravity takes over. It plummets down the side of the mountain, eventually crashing into a much deeper, far more stable valley at the very bottom.
And the fall is the income.
Yes. The massive amount of energy released during that long fall is the dissociation energy, the net difference. The massive violent fall minus the tiny initial upward push is the enthalpy of formation.
So our fuel is just millions of boulders waiting in tiny craters. I love that. And I want you to remember this. Every single time you start your car to drive to the grocery store, or you watch a city bus accelerate away from a stoplight, this exact microscopic accounting ledger is being balanced millions of times a second inside that dark, hot engine block. Tiny craters are being breached by the spark plug, microscopic boulders are violently plummeting into deep atomic valleys, and they are releasing the sheer kinetic energy that moves tons of steel and glass down the highway.
It's breathtaking when you really zoom in and think about the scale of it.
It truly is. It's almost poetic.
And the mathematics behind it, which look pretty intimidating on the page, are actually surprisingly elegant once you grasp the concept. We can actually test this formula right now.
Really?
Yeah, we can be the accountants, build some molecules from scratch on our ledger, and see how the math plays out.
Let's absolutely do it. Let's put this textbook formula to the test, and let's start with a molecule we interact with constantly. Something you are literally breathing out into the room every single second you listen to this deep dive. Carbon dioxide, CO2.
Perfect starting point. To calculate the enthalpy of formation for carbon dioxide, we look at the basic chemical reaction. Solid carbon graphite reacting with gaseous oxygen molecules, which is O2, yields gaseous CO2.
Okay, so grab your mental calculators, everyone. Let's do the math nice and slow. First, we have to list our expenses, the atomization.
Right.
We need to atomize the solid carbon graphite into a gas. If we look at table 11.1 from our source text,
Mhm.
which is this massive master list of bond energies, the atomization energy for carbon graphite is listed as 717.2 megajoules per kilomole.
That's our first expense.
Let's just hold that number in our heads as roughly 700 units of energy we have to pay. Next, we have to atomize the oxygen molecule, the O2, into two separate free-floating oxygen atoms.
Now here's where our source text gets very interesting and, well, a little problematic.
Oh boy. Yeah.
In the step-by-step calculation for CO2, specifically equation 11.5 in the chapter, the textbook authors write down that the atomization energy for oxygen is 435.4. So they mathematically add the 717.2 for carbon and the 435.4 for oxygen to get their total upfront expense. But if you take a close look and flip back one single page to table 11.1.
I have to tell you, I had to read this page 3 times because I thought I was losing my mind or misreading the chart.
I know, it's wild.
The textbook authors actually made a mistake. It's a massive glaring Easter egg for anyone paying really close attention to the math. The text uses 435.4 for oxygen atomization in the CO2 equation, but table 11.1 clearly states that 435.4 is the bond energy for a hydrogen bond.
Yep.
The bond energy for an oxygen double bond, O equals O, is actually 498.2.
This raises an important question, doesn't it? How does a fundamental mathematical error like that make it into a published advanced engineering textbook?
It's crazy. It's a pretty big error.
It really highlights the sheer overwhelming volume of data involved in thermodynamic accounting. When you are a chemical engineer or a researcher dealing with hundreds of different bond energies, cross-referencing massive tables, it's incredibly easy for a human error to slip in.
Yeah, that makes sense.
A tired author or editor probably just grabbed the hydrogen value instead of the oxygen value one row down.
It makes you realize these books are written by humans.
Exactly. So the calculated math in that specific line of the book is actually flawed because they used the wrong input for the expense column.
Right.
But despite that typographical error in the calculation breakdown, at the end of the paragraph, they state that the true accepted tabulated value for the formation of CO2 is negative 393.5 megajoules per kilomole.
Okay, so the final number is correct, even if their work was flawed. And that typo, whether intentional or not, perfectly proves why tabulated empirical data is such a vital safety net for theoretical math, doesn't it?
Absolutely. We calculate these theoretical values using bond energies to understand the mechanism of the universe. It tells us why the energy is released.
Right.
But when we are tasked with designing a rocket engine or a turbine for a power plant, we don't just rely on theoretical pencil and paper math. We actually go into a physical laboratory, we burn a precise amount of the fuel in a heavily instrumented device called a bomb calorimeter.
A bomb calorimeter. That sounds awesome.
It is a great piece of equipment. And we physically measure the exact heat output down to the decimal point. That empirical real-world data, the tabulated value, is the ultimate source of truth.
Because it just measures reality.
Exactly, because it automatically accounts for every microscopic nuance of the universe. And of course, it saves us from typographical errors in textbook calculations.
It's the ultimate reality check on the math. Okay, so CO2 gives us a massive payout of energy, nearly 400 megajoules in the black, which is why burning carbon-based things like wood or coal is so effective at keeping us warm.
Yes.
Now let's look at the other major byproduct of a combustion reaction. When you burn fuel, you don't just get CO2, you get water, H2O.
The ledger for calculating water is fascinating because it forces us to introduce a brand new variable.
Oh, a new variable.
Yeah. So we atomize our hydrogen gas, we atomize half a mole of oxygen gas again, paying those upfront expenses, and we let them violently combine into H2O.
Right, our income.
When they snap together, dropping into their energy valley, they initially form a hot vapor, a gas. The theoretical calculation for forming gaseous water vapor gives us an enthalpy of formation of negative 241.7 megajoules per kilomole.
But hold on a second. When I think of water coming out of an exhaust pipe on a cold day or just water in general, I don't usually think of invisible hot vapor. I think of liquid water.
Sure.
What happens if the exhaust of our combustion reaction cools down and that water vapor condenses into a liquid puddle? Does that physical change of state change our energy ledger?
It changes it significantly. And this introduces the final term in our enthalpy equation that we haven't touched on yet. Latent heat.
Latent heat.
Yeah.
Mathematically written as delta H sublatent.
Right. To understand this, we have to think about what is physically happening during condensation. To go from a chaotic, fast-moving water vapor to a calm, structured liquid water, the H2O molecules have to give up even more energy to their surroundings.
Okay, so they have to calm down.
They literally have to slow their vibration down and allow intermolecular forces to bind them together into a cohesive liquid state.
I really like to think of latent heat as a kind of a shipping and handling fee, or maybe a phase tax imposed by the
A
universe.
phase tax. I love that.
Think about it. You are ordering the exact same chemical product, H2O molecules, but you get a vastly different energy payout depending on whether you want it delivered as a hot gas or a cool liquid.
Yeah.
If it's delivered as a gas, you get your standard payout of negative 241.7.
Yeah.
But if you want it delivered as a liquid, nature taxes the system.
That's a highly accurate way to look at it. For liquid water, you have to subtract the latent heat of vaporization from your ledger.
Okay, what does the math look like for that?
The math in the textbook shows that we must subtract an additional penalty, specifically 18 times 2041.8 adjusted for units. When you apply that extra phase tax, it drops our total enthalpy of formation down to negative 285.65 megajoules per kilomole.
Oh, wow. So it changes a lot.
It does. This means it actually releases more net energy into the universe to form liquid water than gaseous water, because the water molecules have to shed that extra latent heat into the environment in order to condense.
So you, as the listener, can start to see just how incredibly meticulous this chemical accounting has to be. You can't just know the atoms involved.
No, you need the whole picture.
You have to know the exact physical state of matter of your starting reactants, like whether your carbon is solid, graphite, or gas, and the exact state of your end products, like whether your water is vapor or liquid. If you don't track the states of matter, you don't know how much energy is really locked in the vault.
And that meticulous Lego block accounting works perfectly for simple, small molecules like water and carbon dioxide.
Right, because they're pretty straightforward.
Exactly. They're easy to visualize and easy to calculate. But the textbook asks us a harder question. What happens when we start looking at actual usable fuels?
Like what we put in our cars.
Yeah. Molecules that aren't just 2 or 3 atoms sitting in a neat straight line, but complex, sprawling, three-dimensional structures?
Yes, and that is exactly where the simple math starts to break down and get really, really weird. We're moving away from 2D diagrams drawn flat on a chalkboard and entering the complex 3D reality of our physical universe.
It gets messy.
Let's look at a common fuel to see this. Methane, CH4.
Methane is a great example. It is the primary defining component of the natural gas that likely heats your home.
Right.
If you were asked to draw methane on a piece of paper, you would naturally draw a carbon atom right in the center, and you'd draw 4 hydrogen atoms spaced evenly around it. 1 up, 1 down, 1 left, and 1 right.
It looks like a perfectly flat cross, a two-dimensional planar shape.
Right. So let's run the 2D math based on that flat drawing.
Okay, let's do the ledger. Our expenses, we have to atomize 1 solid carbon. Based on our earlier numbers, that's roughly 717 megajoules. Then we atomize 2 H2 molecules to get our 4 single hydrogen atoms. That costs us about 850 megajoules. So we are in the red for over 1,500 megajoules.
That's a big expense.
Huge. Then comes our income. We form 4 identical carbon-hydrogen bonds. Table 11.1 says a single CH bond pays out 414.5.
Okay, so let's multiply that.
Right, so 4 times 414.5 is roughly 1650. You do all the addition and subtraction on the ledger, and you get a calculated theoretical enthalpy of formation of negative 70 megajoules per kilomole.
But then, just like before, we look at the tabulated real-world data from empirical bomb calorimeter testing. The actual measured value of methane is negative 74.78.
Wait.
Yeah. Our calculation is off by almost 5 entire megajoules.
Yeah, that's a huge difference. Why is there a difference when we counted the atoms perfectly?
Because the physical reality is that methane isn't flat.
Wait, it's not a flat cross. Every chemistry diagram I've ever seen draws it like a cross.
I know, the 2D drawings are totally deceiving. Methane is actually tetrahedral in shape.
Tetrahedral, like a pyramid.
Exactly. In 3-dimensional space, you have a central carbon atom, and you have 4 hydrogen atoms surrounding it. But those hydrogen atoms aren't just empty letters on a page. They are surrounded by dense clouds of negatively charged electrons.
And in physics, like charges intensely repel each other.
Right. So those 4 negatively charged electron clouds want to get as far away from each other as physically possible.
And want space.
To get that space, they push themselves into a 3D pyramid shape, a tetrahedron around the carbon core. And because of this specific force 3D geometry, the textbook explains that it creates subtle, microscopic physical interactions.
It's like trying to pack too many magnets into a small box. They're going to twist and push against each other until they find a balance.
Exactly. Chemists call this steric hindrance, or electron repulsion. The atoms are slightly crowding each other in 3D space, which creates subtle, attractive, and repulsive forces between the different parts of the molecule.
Oh, I see.
Simple 2D bond addition, just multiplying a single bond value by 4, simply cannot account for the subtle strain and energy shifts caused by a 3D pyramid shape.
Here's where it gets really interesting. If a tiny molecule, like methane, with just 5 total atoms, can throw off our perfectly balanced ledger just because of its 3D pyramid shape, what happens when we look at something much, much bigger?
Oh, it gets wild.
Let's look at ethanol, C2H5OH. We know ethanol, it's the alcohol in our drinks, but more importantly for this context, it's heavily blended into the standard gasoline that powers our cars.
Ethanol is an absolute beast of a molecule to try and calculate by hand. The scale of the accounting grows exponentially.
How bad is it?
Well, for just one molecule of ethanol, you have to atomize 2 carbons, 6 hydrogens, and 1 oxygen. That is a massive, incredibly expensive upfront energy cost on your ledger.
And then look at the income. The recipe of bonds you have to form is a tangled mess.
It really is.
You have 5 separate carbon-hydrogen bonds. You have 1 carbon bond connecting the spine. You have 1 carbon-oxygen bond.
Yeah.
And you have 1 oxygen-hydrogen bond.
Yeah. It's a lot to add up.
If you sit down, add up all those specific bond energies from table 11.1, subtract it from your massive atomization expenses, our calculated theoretical value comes out to negative 210.7 megajoules per kilomole.
But once again, we check our math against reality. The real-world empirical table says the true value of ethanol is about negative 222.8 megajoules per kilomole.
Wow.
We are off by over 12 megajoules now. The error is scaling up with the size of the molecule.
That is a huge discrepancy. I mean, if I was an accountant and my books were off by that percentage, I'd be fired. Why is the math failing us here?
It brings up a profoundly beautiful philosophical point about engineering, physics, and human understanding. Mathematical models like our accounting ledger and table 11.1 are just maps of reality.
Maps, not the actual place.
Right. They are human constructs designed to make the universe legible. They are not reality itself. When we look at table 11.1, we assign a single, static, unchangeable number to a carbon-hydrogen bond. We pretend every CH bond in the universe is exactly the same.
They aren't.
No. In the incredibly complex 3D reality of an ethanol molecule, the exact energy of a specific bond is slightly warped, stretched, and influenced by the heavy oxygen atom sitting right next to it.
Because it's pulling on things.
Exactly. The three-dimensional spatial arrangement creates a unique microscopic environment full of subtle electromagnetic pushes and pulls. Strict arithmetic can only give us an approximation of this environment.
So the math is just a guess, essentially.
A very educated guess, but yes. It takes empirical testing to capture the true holistic energy signature of the entire structure.
I love that concept. The map is not the territory. The math gives us the underlying mechanism. It proves to us how the energy is stored. But the universe always contains subtle physical complexities that we can't quite capture with simple addition and subtraction.
Beautifully said.
So what does this all mean for our deep dive? It means we have established that physical 3D shapes can slightly tweak the energy vault. But the textbook doesn't stop there.
No, it goes much deeper.
It asks a much harder question. What happens to our ledger when a molecule structure isn't just a complex 3D shape, but is actively, violently shape-shifting at the quantum level?
Now we are entering the incredible territory of resonance. We are looking at molecules that simply refuse to sit still, even when they're supposedly in their deep valley of equilibrium.
This part blew my mind.
The prime example in our source text, and honestly one of the most important structures in organic chemistry, is the benzene ring, C6H6.
Okay, for anyone who hasn't taken organic chemistry, benzene is wild. I want to paint a verbal picture for you.
Go for it.
If you draw benzene on a chalkboard, it looks like a simple hexagon. 6 carbon atoms arranged in a closed ring, with 1 single hydrogen atom sticking out from each carbon corner. But carbon atoms need to form 4 bonds to be stable.
Right.
So to make the chemical bonds work on paper, you have to draw alternating single and double bonds between the carbons in the ring. So going around the circle, it's single bond, double bond, single bond, double bond.
But that simple chalkboard drawing is a complete lie.
A lie?
It is. It's a fiction we tell students just to make the math work out. If you actually examine benzene using advanced instrumentation or analyze its thermodynamic properties, you do not find alternating single and double bonds.
They just aren't there.
They aren't there at all. What you find is that the specific electrons responsible for that second double bond aren't locked into place between two specific carbon atoms at all. They have broken free. They are what physicists call delocalized.
This is hands down my absolute favorite concept in this entire deep dive. I want you to really picture this because it sounds like straight up science fiction.
It really does.
Imagine those 6 carbon atoms in the hexagon are playing a chaotic, incredibly fast-paced game of musical chairs. But instead of chairs, they were passing around electrons.
Perfect analogy.
And instead of the music ever stopping so the electrons can sit down and form a normal bond, the music never, ever stops. The electrons are moving so incredibly fast around that ring that quantum mechanically they are essentially everywhere at once.
Everywhere at once.
They form this continuous buzzing, vibrating ring of pure electron energy hovering just above and below the hexagon structure.
And that buzzing, continuous energy field is what chemists refer to as resonance.
Resonance.
Because those electrons are delocalized and shared across the entire cyclic structure simultaneously, rather than being pinned down between two atoms, it creates a tremendous amount of structural strain and resonance energy.
It's just humming with energy.
The molecule is buzzing with it. It is holding significantly more potential energy than a simple collection of static normal bonds would suggest. And the incredible thing is, we can actually quantify this quantum ghost.
Which is amazing.
Table 11.1 gives the benzene ring a specific measured resonance energy of 150.4 megajoules per kilomole.
It's literally a quantum toast. You can't pin the electrons down to point at them, you can't draw them as a solid line, but their collective buzzing energy is undeniably real, and more importantly, it is measurable.
Highly measurable.
And because it's measurable, we have to account for it as an expense on our ledger. Which brings us, appropriately, to the boss fight of this textbook chapter.
The final test.
It is time to calculate the enthalpy of reaction for benzoic acid. C6H5COH.
This is the moment where we combine every single concept we've learned so far.
Everything.
We are going to calculate not just the formation of a single molecule, but an entire explosive combustion reaction from start to finish. We are going to calculate benzoic acid reacting with oxygen to produce carbon dioxide and water. To pull this off, we use a principle called Hess's law.
Hess's law is beautifully simple in its concept, even if the math is tedious. The enthalpy of reaction, which is the total energy of the explosion, is simply the enthalpy of formation of all your final products minus the enthalpy of formation of all your starting reactants.
Right.
It's basically calculating the final ledger balance after the dust has settled and the explosion is over.
But to get to that final balance, we have to calculate the starting enthalpy of formation for benzoic acid from absolute scratch. And as you said, it is a monster of a molecule. It's huge.
To picture it, imagine a stop sign made of carbon atoms. That's your benzene ring. But hanging off one side of that stop sign is a complex tail made of carbon, oxygen, and hydrogen. That's your carboxyl group, the next the OH.
Okay, stop sign with a tail.
In total, you have 7 carbons, 6 hydrogens, and 2 oxygens to account for.
So we have to go through the massive expenses. Atomizing all 7 solid carbons, snapping apart the hydrogen molecules, snapping apart the oxygen molecule.
So much upfront cost.
Then we calculate the massive income. Forming the 5 CH bonds, 4 regular CC bonds, 3 CCO double bonds in the ring, a CO double bond in the tail, a CO single bond, and an OH bond.
It's a ridiculous, exhausting amount of microscopic accounting.
It really is. But here is the absolute kicker. Because we are dealing with complex shapes, we also have to subtract the resonance energies, the ghosts.
Yes. Because the benzoic acid molecule contains a hexagonal benzene ring, we must subtract the 150.4 megajoules of resonance energy for that buzzing ring of electrons.
And the text notes an even more complex detail. That carboxyl tail group, the COA hanging off the side, also has its own localized resonance energy of 117.0 megajoules. We have to subtract that quantum ghost from the ledger, too.
When you sit down and crunch all those numbers, and I mean all of them, all the atomizations, all the 2D bonds, all the 3D quantum resonance ghosts, the calculated theoretical enthalpy of formation for benzoic acid is massive.
It's a massive number.
And when you finally plug that resulting number into Hess's law, contrasting it against the CO2 and liquid water products we calculated earlier, we arrive at a total calculated reaction energy of negative 365.5 megajoules per kilomole.
That is our theoretical calculation, and let's compare that hard-fought number to the tabulated, empirically tested real-world value from the bomb calorimeter, which is 323.2.
That is an inaccuracy of only about 2%.
It is stunning.
I want you, the listener, to just pause whatever you were doing and appreciate that fact for a second. We took a molecule so incredibly complex it has a massive geometric ring, a sprawling side chain, multiple double bonds, and buzzing quantum resonance fields.
All of that complexity.
And just by using a basic table of simple Lego block bond values, we predicted the explosive energy of that massive molecule with 98% accuracy.
Right.
We didn't burn anything, we just did the math.
Just math.
That is the absolute triumph of this thermodynamic accounting ledger.
It is a stunning validation of the entire chemical theory. It proves beyond a shadow of doubt that the energy of combustion really is stored in the physical chemical bonds, and we have cracked the mathematical code on how to calculate it.
We found the combination to the vault.
We did. And if we connect this to the bigger picture, now that we know how to accurately calculate the exact energy hidden inside individual complex fuel molecules, we can finally zoom out.
Let's do it.
Let's step back from the microscope and look at the macro scale. Let's look at the entire menu of fuels available to mechanical engineers.
Yes. The source text concludes this intense chapter with Table 11.2, which is essentially a global landscape view of common hydrocarbon fuels and their enthalpies of reaction.
It's the grand summary.
It's a menu of how much punch different fuels pack. And when you look at this table as a whole, rather than line by line, some overarching patterns emerge that are, frankly, mind-blowing.
The most striking immediate observation from Table 11.2 is the unbelievable consistency across completely different hydrocarbon fuels.
Okay, explain that.
Whether you were looking at a very light gas like methane, a medium liquid like octane in your car, or incredibly complex, heavy, syrupy diesel fuels, despite having vastly different molecular weights, boiling points, and 3D structures, their enthalpies of reaction by mass are nearly identical.
That is so weird.
If you look at the column for kilojoules per kilogram, they almost all hover right around a plateau of 44,000.
Okay, I have to stop you because I read that and my brain threw a fatal error.
It throws a lot of people off.
Let's unpack this. Why is that true? How can a light, invisible gas like methane, which floats away in the breeze, and a heavy, thick liquid like diesel fuel pack the exact same energetic punch pound for pound? It doesn't intuitively make sense.
It seems counterintuitive until you remember our atomic ledger, because at the end of the day, regardless of the molecule's overall size or shape, you are breaking and forming the exact same fundamental chemical bonds.
Carbon and hydrogen.
Right? Hydrocarbon fuels, by definition, are overwhelmingly made of carbon bonds and carbon-hydrogen bonds. Whether you string 3 of those carbons together in a short chain to make propane, or you string 20 of them together in a massive chain to make heavy diesel, the overall mathematical ratio of those specific bonds to the total mass of the molecule remains relatively constant.
So the ratio is what matters.
Exactly. Therefore, the total energy density by mass hits a hard, unyielding biological and chemical plateau at about 44,000 kilojoules per kilogram. Nature simply maxes out there for hydrocarbons.
That plateau is the physical, unavoidable limit of standard hydrocarbon chemistry. We cannot squeeze any more energy out of carbon and hydrogen bonds than that.
No, we really can't.
And honestly, it also elegantly explains another incredible consistency hidden in the table. Their stoichiometric air-fuel ratios.
Yes, the ratios.
That is the perfect, ideal ratio of air to fuel required for a complete, clean combustion. If you look at the table, for almost all basic hydrocarbon fuels, that ratio hovers in an incredibly tight window between 13:1 and 17:1.
And again, the chemistry dictates the math. Because all these hydrocarbons have that constant ratio of CC and CH bonds, they all require a roughly proportional amount of external oxygen to come in, break those bonds, and form the CO2 and H2O products.
Wow.
It's a beautiful example of microscopic chemistry completely dictating microscopic engineering design. You literally build the size of a car's air intake based on the microscopic bond ratio of the fuel.
That is incredible.
But as with all scientific tables, there is an outlier in Table 11.2 that we desperately need to address: the alcohols.
Yes, alcohols, like the heavy ethanol molecule we built on our ledger earlier, or methanol.
Right.
If you look at their enthalpy of reaction by mass, They're significantly lower than standard non-oxygenated hydrocarbon fuels.
Mm.
They don't even come close to hitting that 44,000 kilojoule sweet spot. They lag way behind. Why are alcohols so much weaker pound for pound?
If we connect this back to our energy ledger, the answer becomes obvious, almost glaring. What is the fundamental structural difference in the chemical formula between a pure, high-energy hydrocarbon like octane and an alcohol like ethanol?
The alcohol has oxygen physically built into it.
Yes.
Ethanol is C2H5OH. It has
Yeah.
that single oxygen atom permanently baked right into the molecular structure.
Exactly. And a standard combustion reaction, the entire goal of the process is to oxidize the carbon and hydrogen atoms to release energy. That's what burning is.
Right.
If the fuel molecule you are pumping into the engine already contains oxygen within its own structure, that specific portion of the molecule is essentially pre-oxidized. That internal oxygen atom is already bonded. It cannot provide any new energy of reaction when it hits the combustion chamber.
It's dead weight.
Complete dead weight.
I couldn't believe it when I realized this. From an energy density perspective, carrying your own oxygen chemically bound to your carbon spine is wildly inefficient compared to just pulling free, abundant oxygen out of the surrounding air as you drive.
It is literal dead weight. It significantly lowers the overall energy density of the fuel per kilogram. It's a thermodynamic penalty you pay for choosing that specific chemical structure. You're wasting space in your fuel tank on an atom that won't give you any payout.
And this brings all this high-level chemistry all the way back down to your everyday life. This is exactly why the gasoline you pump into your car at the station isn't just one pure single chemical.
It's a mix.
If you took a drop of unleaded gasoline and looked at it under a microscope that could see atoms, you wouldn't just see a sea of identical octane molecules. It is a carefully engineered, precisely brewed, complex mixture of dozens of different hydrocarbon compounds.
A very precise cocktail.
Refineries blend different molecules, some with stable rings, some with long straight chains, some highly branched to things, to perfectly balance the volatility, manage the quantum resonance, and hit that exact maximum sweet spot of 44,000 kilojoules per kilogram, all without carrying any deadweight oxygen.
It really is an absolute masterpiece of chemical engineering, entirely disguised as a mundane, everyday commodity that we just pump and ignore.
All right, what a massive, incredible journey this deep dive has been. Let's recap exactly what we've uncovered today.
Let's do it.
We started by realizing that everything you intuitively thought you knew about combustion was entirely upside down. It's not a heater. It's not about adding heat. It's about violent physical transformations.
Yeah.
The energy is already there, trapped in a microscopic vault, waiting for a spark to release the springs.
We learned how to meticulously balance the complex thermodynamic ledger. We accounted for the massive upfront expense of atomization and the incredible explosive income of bond dissociation.
The boulders rolling down the mountain.
Exactly. We saw how complex 3D structures like the tetrahedrons in methane create physical steric hindrance that tweaks the math. And we learned how the phase tax of latent heat docks our final energy payout when we force water to condense from a gas into a liquid.
We even wrangled with quantum ghosts. We tracked down the buzzing, vibrating resonance fields of delocalized electrons spinning infinitely around benzene rings, and we proved that we can predict the explosive power of incredibly massive molecules with 98% accuracy, all to understand the hidden microscopic universe inside a single drop of fuel.
My genuine hope is that the next time you see a fire, whether it's a campfire in the woods, a blue gas burner on your stove, or a massive rocket launch, you don't just see a wash of heat and light anymore. Knowledge is most valuable when it is understood and applied to your view of the world. I hope you look into that flame and see trillions upon trillions of atomic bonds violently snapping apart and reforming, heavy boulders plummeting into deep energy valleys, and nature balancing a complex cosmic accounting ledger right before your eyes.
I know I will definitely never look at a flame the same way again. And to wrap up our deep dive, here's something to chew on long after this conversation ends.
Okay, let's hear it.
As the world races rapidly toward the future, toward carbon-neutral synthetic fuels, advanced hydrogen economies, and sustainable aviation engineers aren't just looking around in the dirt for things that happen to burn anymore.
No, the game has changed.
They aren't just pumping crude oil out of the ground and accepting what nature gives them. They are now acting as literal molecular architects. They are manually balancing this exact ledger of atomization and dissociation energies we talked about today, trying to artificially build the absolute perfect fuel molecule from scratch in a laboratory.
It's the new frontier.
So I leave you with this. If you had the power to play chemical accountant, if you could design a synthetic molecule with maximum quantum resonance, perfectly tailored activation energy, and absolute zero latent heat penalty when it burns, what would that engine of the future even look like?